In this session we are going to discuss about different problems which are related to our wave propagation. So we will start with the basics. So slow by slow we will solve many number of problems in this session. We will start with some simple problems. What will be the direction of wave propagation in a non-magnetic medium in which magnetic field intensity at any point is given by h is equals to 3 cos omega t minus kz ax ampere per meter? Option A, positive x direction. Option B, positive z direction. Option C, negative z direction, and option D, negative x direction. So here to get this simple solution for this problem, just observe the basic equation what is given to us. The basic equation which is given to us is h is equals to 3 cos omega t minus kz ax ampere per meter. Here we need to compare this equation with the standard equation. So what is the standard equation what we have? The standard equation is h is equals to h naught cos omega t minus beta z ay, it is ampere per meter. The standard form of our magnetic field is h is equals to h naught cos omega t minus beta z ay ampere per meter. Just compare the given equation with this equation. If you are comparing this equation, then h naught is equals to 3, that is nothing but the amplitude of our magnetic field. So clearly write down that h naught is equals to 3, and omega t both are same, that omega is the angular frequency and this time is the time period. Next, instead of beta he has given k, so no problem that we can take any constant k. And clearly if you take this one, this is nothing but the direction of our wave propagation. So with the standard equation, if you are comparing that one, the direction of our wave propagation is here clearly positive z direction, right? So the direction of wave propagation is positive z direction. Just what we are doing is we are comparing the equation with the standard equation. But here clearly observe, in the equation which is given to us that we have the component in x direction, in our standard equation we have the component in y direction. No problem, the component may be either in x direction, y direction and z direction, that's purely depend upon the requirement. So here clearly the magnetic field what we have may be in x direction or maybe in y direction or maybe in x direction, that don't bother about that one. The direction of wave propagation is clearly positive z direction. Here what I do is just I will give you a blind tip. Whenever you find minus some quantity here, clearly remember that that is a positive, that quantity, that is nothing but positive z direction. If you find plus here, in this case if you find plus, then that will be the negative z direction. Okay, clearly remember that simple step. So here clearly the answer is a positive z direction, the wave is propagating in positive z direction. This is the answer. Question number 2. E dot h of uniform plane wave is option A EH, option B 0, option C eta into E square, option D eta into h square. Here a very simple problem which is given to us is E dot h of a uniform plane wave was asked. That E dot is equals to how much, that what we are supposed to analyze. But here clearly the wave given is a uniform plane wave. Since it is uniform plane wave, the electric field and magnetic field what we are considering will be on a plane. And what will be the relation between them with respect to the angle? That clearly electric field and magnetic field are perpendicular to each other. Since the electric field and magnetic field are perpendicular to each other, the dot product between two perpendicular vectors or the two normal vectors is always equals to 0. So here the asked quantity is E dot h, the dot product between two perpendicular quantities, which must be equals to 0 for a uniform plane wave. So option B, that what we have in the problem is correct answer. So this is a simple solution for this question. The depth of penetration in free space is dash. Option A infinity, option B 1 by alpha, option C 0, option D small. Here the asked quantity is depth of penetration in free space. So before that, just recollect what is depth of penetration. Depth of penetration is nothing but the distance travelled by a wave to attain 36.8% of its initial value. That for that we have a simple equation that it's denoted with delta, and we have a simple equation for that, that is delta is equals to so the depth of penetration for any medium is equals to delta equals to 1 by under root pi f mu sigma. So if you substitute the corresponding values which are meant for the medium what we are considering, that is nothing but free space, we will get the value of this delta. For free space, now observe clearly, this mu is nothing but free space permeability mu naught and sigma is simply equals to 0. So if you substitute sigma is equals to 0 here, then what we will get? Delta is equals to infinity. That what we can understand from this result is a wave can travel for infinite distance to attain 36.8% of its initial value in free space. That practically what you can say is the wave can travel for very long distance in the free space. That's why we will consider this free space as the most useful medium for electromagnetic wave propagation. So option A, that what we have in our options is right. So this is the simple solution for this question. The electric field of a uniform plane electromagnetic wave in space along the positive x direction is given by E is equals to 10 ay plus j az e power minus j 25x. The frequency and polarization of the wave respectively are option A 1.2 GHz left circular, option B 4 Hz and left circular, option C 1.2 GHz and right circular, and option D 4 Hz and right circular. Now here clearly observe what is the quantity which is given to us. The quantity which is given to us is the electric field intensity which is given as 10 ay plus j az e power minus j 25x. And in the problem he mentioned clearly that it is travelling in positive x direction. And he asked to observe what is the type of polarization and what is the frequency of our wave. To observe this one, we have a simple procedure, we will discuss that one. Before that, let us examine whether the wave is travelling in positive x direction or not. And clearly observe here the wave equation has no time parameter, that here the time constant was suppressed, the time parameter was suppressed. So what we do is we will try to incorporate the time constant or the time parameter to get the original wave equation, right. So E can be written as E is equals to 10 ay plus j az e power minus j 25x e power j omega t, that the suppressed time constant was added by me for our proper form. So which is equals to 10 ay plus j az. Here what I am doing is I am considering this as a single one, j omega t minus 25x, and then divide this quantity 10 e power j omega t minus 25x ay plus j 10 e power j omega t minus 25x az. Just what I did is I divided this e power some quantity to this, I have applied this quantity to these two terms, that the first term which is in y direction, the second term which is in z direction, that what I am considering as two components of the electric field. Here the electric field can be once again divided as two components which is in y direction and which is in z direction. Now if you want to get the exact electric field equation, what we do is we will try to consider always the real part of this one. Then what we get is a uniform equation and the simplified solution we will get for that. So try to get the real part of these two terms, that e power j theta is nothing but cos theta plus j sin theta. Here also this is e power j theta cos theta plus j sin theta. After dividing and multiplying, in this one the real term what we get is 10 cos omega t minus 25x in the direction of y. That is the real term which is remains for this. Don't think that I am writing directly. What I am doing is I am taking the real term from this particular quantity. Here also what we have is initially j multiplied with j for sin, what you get is the minus, and that is the real term, right. So here also I am considering the real term. Now that can be written as minus 10 sin omega t minus 25x az. So this is the exact equation of electric field what we are going to analyze. If we analyze this equation, then we will get what is the type of that polarization, what will be the frequency. Now compare this one with the original or standard equation. If you are comparing the standard equation, so what we have, this is 10 cos omega t minus beta x, that what you can say, that is nothing but beta is equals to 25, that what we got from this equation directly. And as I said in our previous problem, whenever you find a negative sign here, immediately you can recollect that it is traveling in positive direction. Positive which direction? X direction it is traveling. So in the problem the data was given correctly. So clearly here also we can find a negative x, that is nothing but positive x direction it is traveling, right? So directly from this particular equation we can say that the wave is traveling in positive x direction, and it has two components, one is along y direction, another one is along z direction. So independently I am writing those two equations as Ex and Ey and Ez. Ey is equals to 10 cos omega t minus 25x, that is nothing but the y component I am writing here, and z component Ez is equals to minus 10 sin omega t minus 25x. Now to observe what is the type of polarization, here we need to take the amplitude of these two equations, these two components, and the phase difference between these two components, that what we are supposed to observe. Initially try to observe the amplitude. Here the amplitude for y component is 10, the amplitude for z component is also 10. That is clearly y component and z component have same amplitude, right? Next, go for the phase difference between these two. Here what we have is a cos term, and here what we have is a sine term. Since we have exactly pi by 2 phase difference, a conclusion can be taken like this: all the components which are in our electric field, that is nothing but y component and z component, have same amplitude and pi by 2 phase difference. Since we have same amplitude and pi by 2 phase difference, clearly we can say that it is a circularly polarized signal. So in the option we need to identify very circularly polarized signal, and most fortunately we have in all options we have circularly polarized signal. So clearly remember that, so from the basic analysis, circularly polarization, that what we have observed. Next we need to identify whether it is a left-handed circularly polarized or right-handed circularly polarized signal. At a particular space, for different values of time, we have to identify where the components are. That the electric field is in which direction at a given time, that what we have to identify. For that, here don't go for any other analysis, just I will give you a simple step, that at a given location will be treated as zero location, that x is equals to 0. If we put x is equals to 0, then Ey and Ez equations will be like this. Ey is equals to 10 cos omega t, that here clearly remember I am considering this one at a fixed location, that is at x is equals to 0, right? And Ez is equals to minus 10 sin omega t. Ez is equals to minus 10 sin omega t. So here what we are doing is we are observing the wave at a fixed location. Next, as the time moves, that is the time increases, where will be the electric field and how it takes rotation, that what we require. So what I do is initially I will take 0 time, that at 0 time what will be the electric field intensity we are observing. Just for that, for our convenience, I will take this entire omega t is equals to 0, right? So yet omega t is equals to 0, then clearly if you observe among these two only Ey will exist, right? So at initially if you observe the electric field, that will be along y direction, Ey will exist means that is along only y direction, and the time moves on, that is we are increasing the time. If you are increasing the time, take an appropriate time and substitute there. For our convenience, what I am doing is I am considering omega t is equals to pi by 2, that omega t equals to pi by 2. Here remember always we are supposed to take the positive time, there will be no negative time, right? So as the time increases, as omega t is equals to pi by 2, if you are substituting pi by 2 instead of this one, what you get is Ey is equals to 0 and minus Ez will exist. And clearly observe here what's happening. At initial time, that at a time t is equals to 0, Ey will exist. as the time moves on, minus Ez will exist. So what you can say is the vector is taking a rotation from y to negative z. You can say the same statement like this: the vector is taking rotation from z to y, right? Y to negative z or z to y. If you recollect this one, simply this follows a left-handed screw principle. Since it is following a left-handed screw principle, we can say that the circular polarization what we observed earlier is nothing but the left-handed circularly polarized signal. So clearly the type of polarization what we have for this type of wave is a left-handed circular polarization of the signal. That's what we have observed. Now we are going to calculate the frequency of this signal also. So to calculate the frequency, what we are supposed to consider? Here just observe what are different parameters which are given to us in the equation. Different parameters which are given to us in the equation are: beta is given, right? Omega is given, the amplitude is given. Among all these, which one is most suitable to calculate the frequency, right? So consider beta is equals to 25, and here clearly the wave is traveling in which medium? The wave is traveling in free space. Since the wave is traveling in free space, let us take the phase velocity of that one as equals to the light velocity. That is, the phase velocity Vp is equals to c, which is nothing but 3 into 10 power 8 meter per second. So this is only the data what we have from that equation. So using this beta and Vp, can we identify omega? Yes, exactly. So we have a relation between Vp, beta and omega. That what is that equation? Phase velocity Vp is equals to omega by beta. That phase velocity can be calculated with these two. That omega is nothing but 2 pi f. So 2 pi f by beta is equals to phase velocity. That what I am considering to get the frequency of our signal. So simply substitute omega equals to 2 pi f divided by beta. How much we got beta from the equation? 25. 2 pi f by 25, which is equals to phase velocity. Phase velocity is nothing but 3 into 10 power 8. 3 into 10 power 8. After simplification of this one, so what we get is the frequency. So with a simple approximation method and a simplification, the frequency what we get is f is equals to 1.2 gigahertz. So here clearly the answer what we got is left-handed circularly polarization, and the frequency is 1.2 gigahertz, and in the options, option A is our correct answer. So this is a method of identifying type of polarization and calculating different parameters which are required for us from the given equation. Here initially we are supposed to identify what are different parameters which are existing in the equation, and later we need to identify what are the quantities we require. So closely we have to observe them and just correlate them to get the correct answer. This is the solution for this question. We will move to next one. The electric field component of a time harmonic plane EM wave traveling in a non-magnetic lossless dielectric medium has an amplitude of 1 volt per meter. If the relative permittivity of the medium is 4, the magnitude of the time average power density vector in watt per meter square is. Here the electromagnetic wave is traveling in a non-magnetic medium. That here clearly, since whenever the data was mentioned like this, remember that take mu is equals to mu naught. Since it is a non-magnetic medium, there will be no effect of relative permeability. That's what you can say. So consider mu is equals to mu naught, keep it aside, whenever it is useful we can use that one. And the wave is traveling in a non-magnetic medium has the electric field intensity E is equals to 1 volt per meter, and the relative permittivity epsilon r is equals to 4. That we are supposed to calculate the time average power density. That whenever the word power density was mentioned, clearly recollect that power density is equals to power per area. That's why he clearly mentioned that power density in watt per meter square he is asking, right? So here we are supposed to calculate the power density. That power density can be calculated easily from our Poynting vector and the Poynting theorem. So how you can calculate the time average of our power density? That the time average power density PAVZ can be directly taken as 1 by 2 if it is in vector notation E cross H star. Clearly remember, if you want the vector, E cross H star is the equation that what we are supposed to use. But here we require only the magnitude. That's why instead of that cross product, what I do is I will take the magnitude of those two. That simply it is equals to 1 by 2 magnitude of E magnitude of H. But here the H was not given to us. Instead of H, only E was there. So what we have to do is just we have to take this H, or we have to bring this H from the given data, right? As I said, since the medium is a non-magnetic medium, consider mu is equals to mu naught. Then how we can obtain H from the given data? That we have a relation, there is no possibility to get H. So because what we do is we will convert that H to E. That is better thing. So what is the relation between E and H? Already we know E by H is equals to intrinsic impedance of the medium. That what I use here. So clearly write down here. So E by H is equals to intrinsic impedance of the medium. Clearly remember, this is not free space. Don't write E epsilon eta naught. Right? So E by H is equals to eta is only the quantity what we are supposed to consider. Now how you can calculate this eta? We have a basic equation for calculation of eta, that is under square root of j omega mu divided by sigma plus j omega epsilon. That is the formula that what we have to use. And here clearly the mentioned medium is a lossless medium. Since it is lossless medium, sigma is equals to 0. Substitute sigma is equals to 0 here. Then j omega mu divided by j omega epsilon, which is equals to under root mu by epsilon. Now for our medium, mu can be replaced with mu naught, that square root of mu naught divided by, now epsilon is nothing but epsilon naught into epsilon r. Epsilon r is given as 4. That's why here I will consider 4 epsilon naught, that is epsilon naught into epsilon r. So which is equals to simply 1 by 2 under root of mu naught by epsilon naught. This mu naught by epsilon naught is a constant, that is a free space characteristic impedance, which is equals to 120 pi. So directly substitute 120 pi here, then what we get is just 60 pi. 120 divided by 2 is 60 pi. So the characteristic impedance of the medium is known to us. So E by H is equals to eta, that is nothing but our 60 pi. Now from this one, H is equals to, directly you can write E by 60 pi. So don't go for any other equations. Don't try to get magnetic field intensity equation from the electric field intensity equation. Just use these relations. That E by H is equals to 60 pi corresponds to H is equals to E by 60 pi. Substitute here. Then which is equals to 1 by 2 magnitude of E, and instead of H what I am writing is magnitude of E by 60 pi, which is equals to magnitude of E square by 2 into 60 is 120 pi. Now substitute the magnitude of E here. The magnitude of E is 1 volt per meter. Directly substituting 1 volt per meter here will gives us 1 divided by 120 pi, and power average we are calculating once again, power density average. So the units are watt per meter square. So if you observe, so option C is correct in our options. That option C has the same one, that is 1 by 120 pi watt per meter square. This is a simple solution to this problem. Question number 6. A plane wave having electric field component EI is equals to 24 cos 3 into 10 power 8 t minus beta y AX volt per meter, and traveling in free space is incident normally on a lossless medium with mu is equals to mu naught and epsilon is equals to 9 epsilon naught, which occupies the region y greater than or equals to 0. The reflected magnetic field component is given by, here the given wave is traveling in free space initially and it is traveling clearly in positive y direction. That from the equation itself we can observe that it is traveling in positive y direction, and it hits a boundary, that a dielectric medium appears while it is traveling, it hits the dielectric medium and reflects. So here we require what will be the equation of that reflected magnetic field. Incident electric field is given to us. Whenever it hits the boundary of our dielectric and free space, it takes reflection, and we require what will be the equation for our reflected magnetic field. So here we are supposed to observe initially what will be the direction and what will be different components which may exist for that reflected wave. Right, here clearly imagine. So here what I am doing is I am showing the fingers for the direction, electric field and magnetic field, direction of wave propagation, electric field and magnetic field. Let us take, so this is direction of wave propagation. So if this is direction of wave propagation, then you may think that this may be the electric field or magnetic field, this may be the electric field or magnetic field. But here clearly we are supposed to take the right-handed screw principle. Even though I am showing left hand, we are supposed to consider the right-handed screw principle. That this is X, Y, Z. Okay, once again, this is X, Y, Z. The wave is traveling along or Y direction and the electric field is along X direction. That AX represents always X direction. That this is the electric field direction. That what we have, right? And this may be the magnetic field direction. Now clear that this is our Y, X and this is our Z. The wave is traveling along Y direction. The electric field has X and the magnetic field is along, that may be along Z direction. That what we are supposed to observe. So in the answer, if we are supposed to take the direction of our magnetic field, we need to add the direction of our magnetic field as Z. Don't take that one as X, because the electric field is in X direction, the wave is traveling in Y direction, the magnetic field may be definitely along Z direction. Right? Clear? Now imagine the wave is traveling like this. It hits the boundary. It is traveling in positive Y direction initially. Right? So whenever we are considering the positive Y direction, we will get a negative sign here. That what we have. So it is traveling in positive Y direction. It hits the boundary and it takes reflection. Right? Imagine that one. It is traveling in positive Y direction. It hits the boundary. It takes reflection. While it is reflecting, what are the components which are varying? While it is taking reflection, the components which are varying are the direction of wave propagation. Initially it is traveling in positive Y direction. Now it is traveling in negative direction. Right? So clearly whenever we are writing the reflection wave, we are supposed to write down the wave is taking a propagation in negative Y direction. Remember that point. And whenever it is taking a reflection, here clearly this finger doesn't vary. It is in the same direction, same as our previous one. That the magnetic field direction is incident and reflected, both are same for magnetic field. But this finger is varying its direction. Initially this finger is in this direction, after reflection it is in opposite direction. Clear? So clearly what we have to do is we have to observe different directions like this. Wave is traveling initially in positive Y direction. It hits the boundary and it reflects. Whenever it is reflecting, it is traveling in negative Y direction. And clearly this finger doesn't vary, that is the magnetic field incident and reflected, both are in same, both have same component. And the electric field initially it is in positive X direction, but after reflection this will be in negative X direction. Right? So with these basics, just we will try to write down the equations. Now clearly observe, initially the wave is traveling in free space like this in positive Y direction. It takes a reflection and the reflected wave will be traveling in negative Y direction. Here the medium has epsilon is equals to 9 epsilon naught and mu is equals to mu naught. Here the medium is free space, therefore epsilon is equals to epsilon naught and mu is equals to mu naught. Now the incident wave we have, since we have incident wave, we can obtain the reflected wave with the help of reflection coefficient. So how to obtain the reflection coefficient? Reflection coefficient gamma is equals to, we have a basic equation eta 2 minus eta 1 divided by eta 2 plus eta 1. That the characteristic impedance we are supposed to calculate now. So what is eta 2 here? That eta 2 is equals to, since it is a lossless medium, directly write down, don't go for any other analysis, mu by epsilon. That mu is nothing but mu naught divided by epsilon is nothing but 9 epsilon naught. So if you take this equation under root of mu naught by epsilon naught is 120 pi. So directly write down here 120 pi divided by 3. Since under root is equals to 3, directly you can write that one as 120 pi by 3, which is equals to 40 pi. So the characteristic impedance of the second medium, what we are observing is 40 pi. Then what will be the characteristic impedance of our first medium? Since it is free space, it is 120 pi, right? Now substitute here, which is equals to 40 pi minus 120 pi divided by 40 pi plus 120 pi. So which is equals to 40 pi minus 120 pi is minus 80 pi divided by 160 pi, which is equals to minus 1 by 2. We got the reflection coefficient, and we have what is the basic definition of that reflection coefficient? It is the ratio of reflected electric field to the incident electric field. Simply this can be taken as ER divided by EI, right? So ER by EI is equals to minus 1 by 2. Already what we have is here EI. Now substitute there, then what we get is ER. Therefore ER can be written as ER is equals to minus 1 by 2. Directly what I do is step by step I will substitute all the parameters. What will be the amplitude? 24. As it is, the amplitude will be transferred as 24, and the basic form is cos form. Cos will not vary, don't vary this one, this is cos, and the remaining parameters like 3 into 10 power 8 t minus beta y I am writing, but here I want to change this. Recollect the analysis that what we did. The analysis is, since it is a reflected wave, it is traveling in negative y direction, it is not traveling in positive y direction. So here instead of taking a negative, we are supposed to take positive. Clearly remember that. So whenever we have a positive here, that it is traveling in negative y direction. Since it is a reflected wave, it is traveling in negative y direction. And in that analysis, that E field component has taken opposite direction. The reflected wave has opposite to the original. The original is in the direction of AX. So the reflected will be in the direction of minus AX. Volt per meter. Just observation is required here. Don't go for any calculations. Here whenever the wave hits the boundary, it takes reflection. So the direction of wave propagation changes. That's why here I am writing plus. Instead of minus, here I am writing plus. And the field component direction also changes. Initially it is x direction. Whenever it is taking reflection, it is in negative x direction. Right? This is our ER. Now what is the relation between ER and HR? We have a very simple relation, that ER by HR is equals to eta. Simply ER by HR is equals to eta, characteristic impedance of the medium. So what will be the characteristic impedance of the medium? Here since it is free space, the characteristic impedance of the medium is eta naught, 120 pi. So clearly from this equation, HR is equals to ER divided by eta naught. That take this ER and substitute here, which is equals to, after simplification, negative into negative, it's what you will get is a positive. 2 goes 12 times here. So 12 cos 3 into 10 power 8 t plus beta y divided by, that is the entire ER I wrote here, eta naught is 120 pi. And what will be the direction of this HR? That here we are supposed to represent the unit vector also, right? Now once again recollect that the wave is traveling in y direction, it hits the boundary, it takes reflection. So the reflected wave is traveling in negative y direction. The field component of electric field was varied, but the direction of magnetic field was not varied. Initially it is in z direction, after reflection also it is in same z direction. That's why I am adding a unit vector a z here. Don't go for any calculations once again. Here you may have some complex formula, don't go for that, just analysis is required here. So after simplification, what we get is just 1 by 10 pi cos 3 into 10 power 8 t plus beta y az ampere per meter. So this is the answer that what we require. So clearly from this problem what we can understand is, whenever the electric field intensity or the magnetic field intensity, whatever it may be the given, here we need to observe what are different conditions and parameters and constraints which have while the wave is propagating. Whenever it hits the boundary, what will be the direction of reflected wave? Whenever it is taking a reflection, what will be the reflection coefficient? How that reflection coefficient will be useful for obtaining the remaining wave equations? So here clearly what we have to do is just we have to observe what are different parameters which are involved in the problem, and from that we are supposed to get the reflected magnetic field, so using all those parameters. So this is the answer. The H field in ampere per meter of a plane wave propagating in free space is given by H is equals to AX 5 root 3 by eta naught cos omega t minus beta z plus AY 5 by eta naught cos omega t minus beta z plus pi by 2. The time average power density is, options are given as option A eta naught by 100, option B 100 by eta naught, option C 50 eta naught square, and option D 50 by eta naught. Here for a uniform plane wave, the H was given to us. H is equals to AX 5 root 3 by eta naught cos omega t minus beta z plus AY 5 by eta naught cos omega t minus beta z plus pi by 2. We require the average power density. But once again recollect that power density always stands for power per area and the units are watt per meter square. So whenever we have a power density, just recollect the pointing theorem and pointing vector. So average power density is equals to simply 1 by 2 E cross H star, right? That we can write that one as in terms of magnitude, just 1 by 2 into E multiplied with H. The magnitude of E and H we are supposed to consider. And here there is no E, we have only H. That we need to convert that E term into the H. That we have a relation between them. So what is the relation between E and H? The magnitude of E divided by magnitude of H is equals to eta. That what I consider here. So magnitude of E divided by magnitude of H is equals to eta naught. That since the wave is traveling in free space, directly I am considering this one as eta naught, where E and H are not vectors, they are magnitudes only. That E can be directly taken as E is equals to eta naught multiplied with H. So what I do is I will try to use this result in our pointing vector. That the power average, P average is equals to 1 by 2. Instead of E, directly I am writing eta naught H, correlate that one, and H can be written as it is. So which is equals to 1 by 2 eta naught magnitude of H square. That what we have. So what will be the magnitude of H? That consider the H has two components. One is in X direction, another one is in Y direction. So the resultant magnitude we require. That magnitude of H is equals to, directly we can consider this one as under root of that X component square plus Y component square. The magnitude of X component is 5 root 3 divided by eta naught whole square plus, and Y component, that is 5 divided by eta naught square, which is equals to, so if you take this one 5 root 3 whole square, which is 75 plus 5 square, 100 divided by eta naught square under root of 100 divided by eta naught square. That is what we have is the magnitude of H. Now substitute this magnitude of H here. So H square directly can be written as 100 by eta naught square. Therefore the average power is equals to 1 by 2 eta naught multiplied with H square. H square is 100 divided by eta naught square. So eta naught will be cancelled. So 1 eta naught remains for us. 2 will be cancelled for 50 times. Then simply it is 50 divided by eta naught, and the units are clearly watt per meter square. So if you obtain this answer, clearly this is matching with our option D. So in this problem 50 by eta naught, option D is correct answer. This is a very simple problem. The magnetic field intensity vector of a plane wave is given by H of x, y, z, t is equals to 10 sin 50,000 t plus 0.004 x plus 30 ay. The wave propagating with a phase velocity of, the options are given like this. Option A 5 into 10 power 4 meter per second. Option B minus 3 into 10 power 8 meter per second. Option C 1.25 into 10 power 7 meter per second, and option D 3 into 10 power 8 meter per second. Here clearly observe, the given quantity is the magnetic field intensity. The magnetic field intensity is a function of time and it is given as 10 sine 50,000 t plus 0.004 x plus 30 ay ampere per meter. If you understand this one, what is the quantity and what is each and everything in that particular one, the problem is very simple. Just compare this one with the standard one that what we have. The standard equation that what we have for magnetic field is H is equals to H naught sine omega t plus or minus whatever it may be, minus beta x or z or y whatever it may be, plus some phi, right? That is the standard form that what we have. Here clearly if you are observing, this quantity that what we have must resemble omega with the standard equation, and the quantity here that what we have is nothing but the phase constant beta, and this 30 is nothing but maybe 30 degrees phase difference with respect to the electric field that what we have, and the H has y component only. So this is a simple representation of our magnetic field equation, and we have some numerical values. Now we require the phase velocity. The phase velocity is described as omega by beta. Directly we have omega here, so take this one, that is 50,000 divided by beta is 0.004, and if you solve this one, simply what we get is 1.25 into 10 power 7 meter per second, and in our options, option C is correct for this question. It's a very simple one. Just we need to identify what are different parameters which are existing in that particular problem and take the relevant equation. Vp is equals to omega by beta will directly give us the answer. The depth of penetration of EM wave in a medium having conductivity sigma at a frequency of 1 MHz is 25 cm. Then the depth of penetration at a frequency of 4 MHz will be, the options are given like this. Option A 6.25 cm, option B 12.5 cm, option C 50 cm, and option D 100 cm. Here clearly observe, for a given material some conductivity is there. Since conductivity is there, definitely you are supposed to calculate the depth of penetration. If there is no conductivity, directly the depth of penetration is infinite, right? That's why in the problem he clearly mentioned that for a material with conductivity sigma. So clearly observe that point, right? At some frequency f is equals to 1 MHz, the depth of penetration is 25 cm. And at another frequency 4 MHz, we require the depth of penetration. So we require the relation between this delta and f. How this depth of penetration or the delta was defined. So once again recollect what is the basic definition. It is distance traveled by the wave to attain 36.8% of its initial value, and we have some equation for that. So write down the equation of delta. So delta is equals to 1 by under root of pi f mu sigma. That clearly this delta is inversely proportional to square root of the frequency. So write down the relations. Delta 1 is inversely proportional to 1 by under root of f1. Delta 2 is proportional to 1 by under root of f2. So if you are taking the relation between them, just you multiply them, then what we get if you are multiply or divided, if you divide them, that delta 1 divided by delta 2 is equals to, clearly you can say that it is f2 by f1. So the inversely proportional relation will applicable here. So delta 1 divided by delta 2, what is delta 1 here? 25 cm at 1 MHz frequency. So directly take 25 cm divided by, we don't know what is delta 2, so directly take this one as delta 2, which is equals to under square root of, what is f2? 4 MHz. What is f1? 1 MHz. So 4 divided by 1 I have to write here, mega will be cancelled, so 4 divided by 1. So clearly from this relation you can say that delta 2 is equals to 25 by 2, which is equals to 12.5 centimeter. So clearly the depth of penetration when you are increasing the frequency was reduced. So whenever we are taking the high frequencies that can travel for less distance in a particular medium which has some conductivity. That's why we are not transmitting, or we are not using any conducting medium for transmission of our electromagnetic wave. That is the observation that what we can take from this problem. So as the frequency increases, the depth of penetration is decreasing. Now if you take the options, option B, that what we have is right for this question, that is 12.5 centimeters the answer. A plane wave is characterized by E is equals to 0.5 ax plus ay e power j pi by 2 multiplied with e power j omega t minus beta z. The wave is dash, that options are given like this: linearly polarized, option B is circularly polarized, option C elliptically polarized, and option D is unpolarized. Here clearly the electric field is given to us. The electric field E is equals to 0.5 ax plus ay e power j pi by 2 multiplied with e power j omega t minus beta z. Just examine that equation. What are different parameters which are existing in that particular electric field? And clearly the polarization will be obtained or examined for electric field only. Right? Now here in this expression, the electric field E has two components. One is along x direction and another one is along y direction. So whenever we are supposed to observe the type of polarization, we must observe the amplitude of that coefficients and the phase difference between the components. Right? Now examine the amplitude. For x component, what we have is 0.5. So directly I am writing here the magnitude of Ex is equals to 0.5. Now observe the magnitude of y component. The magnitude of y component is just 1. That the magnitude of Ey is equals to 1. And is there any phase difference between these two? Examine for that. Here clearly we have one more term, that is e power j pi by 2. Since we have this e power j pi by 2, definitely after expansion we can say that between these two we must have some phase difference that is equals to the pi by 2. So clearly the phase difference that what we have is pi by 2. Now with these conditions, just examine what is the type of that polarization. What we have is different amplitude and the phase shift is, or the phase difference between these two components is pi by 2. So with the compilation and the recollection of our data gives us, this will gives an elliptically polarized signal. So clearly different amplitude, phase shift is pi by 2, elliptical polarization. If suppose in the same problem, if the amplitudes are same, then clearly we have to say that it is a circularly polarized signal. But here the amplitudes are not same. Therefore the answer is elliptically polarized signal. In our options, if you observe, option C is correct option for this particular problem.